Well, hello, my name is Celso. I'm from the Structural Dynamic and Acoustic System Laboratory at UMass Lowell, and I'm here today to present our project, which is Optical-Based Structural Health Monitoring of Truss Bridge. I hope you all enjoy. Thank you for watching. So regarding the motivation for project, why do we want to use cameras instead of the traditional sensing techniques, such as accelerometers that we currently have? The first thing that comes to mind is regarding the portability of the cameras. If you're using a traditional data acquisition system, you probably need to place all the accelerometers on the bridge, taking a considerable amount of time. Also, you probably have to have a dedicated system for each structure that you're monitoring. While the camera, you can just place on the right location, record the video, and you're ready with your testing. In addition, the cameras can extract a full field mode shape of the structure, while the accelerometers, even if you have 100 of them, you have just a discrete mode shape. Also, with the camera, you can actually access the dynamic information at any given point of the bridge. Okay, but how can we extract motion from videos, frames, or images? So starting with the phase correlation and motion extraction, if you have two figures with a displacement between them, such as figure 1 and 2. So if we take the Fourier transform for both images, we get a frequency domain graph as the second one here. Then applying a cross-power spectrum, which is a correlation on how similar those two signals, or in this case, those two images are, we get an even different plot or another graph. Applying then the inverse Fourier transform for this graph, we can obtain a new time signal, and locating the peak of this new signal will actually be the exactly same location of the difference of those two images. So for instance, when calculated for those two images, the result would be 51 pixels, which is the displacement between the patterns between them. So now that we know that we can actually extract motion from two different figures, if we have a video is basically many frames taken in the time domain. So going back here on the top, we can extract a different motion at any given time, and then applying a Fourier transform on this time domain series, we can get a new frequency domain with the natural frequencies of what we're observing. And that is basically how works the phase-based motion extraction. For this project, we're using phase-based motion extraction and phase-based motion magnification. So basically for our phase-based motion magnification, if you have a video y of x, y, and t, where the x and y are the positions of the frames and t is the time of the frames, we can then convolute, which is this technique explained here on the bottom, with the Gabor wavelets, and that will give us a equation of the form of an amplitude times an exponential of phi angle. Nowadays, it's well known that this phi angle contains the displacement and the position information of the frames. So then we can apply a bandpass filter, and with this bandpass filter, we can select, for example, the first natural frequency or the second natural frequency of our frequency, and then multiply that by a magnification factor, beta, for example. Then we can generate a new phi of UV and T, and going the process backwards, you can get a video with the motion magnified. So with those techniques of phase-based motion extraction magnification, we can go for our experimental implementation. So for our laboratory scale test, we induced artificial damages on the bridge in order to verify the change of the natural frequency due to damage. So for that, we used first a health case scenario where the bridge didn't have any kind of damage and extracted the first natural frequency of this bridge. Later, we induced two different types of damage. The first one was the light damage, as we can see here on the image in the middle, where we changed the material of one of the members of the bridge for a light one that has less stiffness. With that, we could observe that there is a change of the natural frequency from 8.37 Hz to 8.02 Hz. We also did severe damage case scenarios where we actually removed parts of the bridge and then monitored what happened to the bridge. So for this severe damage case, we did two different damages. The first one, we took the bottom member of the bridge. The second one, we took the middle member, and finally the top member, and then analyzed the change of the frequency for all cases. And as we can observe here, there is a significant change on the natural frequency when we have a severe damage. The biggest change was when we removed the top member, that the natural frequency shifted to 6 Hz. We also did a test on a real truss bridge, as you can see here on the figure on the bottom. This is a working bridge close to the UMass campus, and it's under the normal operational conditions. So there's traffic, wind, and all kinds of excitation. Our main objective here was to verify if we could extract information of a real truss bridge under normal working conditions. So a variation of light, and for this case, we didn't have an ideal position for recording. So those two boxes in red are the locations that we analyzed the movements. And as we can see here, we could extract the first bending mode shape at 2.3 Hz, and then modulations of 4 Hz varying from 8 to 20 Hz. Those other peaks are probably due to nonlinearities of the bridge or other types of excitation that's known traffic related, such as wind. So in order to increase the accuracy of the damage detection, we wanted to do data analysis via artificial intelligence. So for that, we're looking now to the mode shape instead of the natural frequency of the structure. And we're using convolutional neural network to extract a pattern of the full field mode shape under those different conditions. So the convolutional neural network takes a big sample of images and then divide those images in a matrix, in many matrices, and try to find a pattern between them. So that's what we're doing with the mode shape of the structure. So for that, we did a pre-processing of the frames, taking first the frame with the motion magnified, and then extracting just the motion between those shapes because those images are very similar. So for that, we took one of the frames as our base and static view, and then extracted the difference between those frames and the next ones, giving some image like this one on the middle. After that, we increased the contrast, so we have more data to work, as you can see on this image. And finally, to enhance our algorithm, we did some data augmentation. So as we don't want to see where the damage is, we want to see the difference on the mode shape itself. We selected regions that we don't have the severe damage exposed, and then move the image and rotate those images, as we can see here on the bottom, in order to train our model. In conclusion, we can say that video-based sensing techniques has a good potential to extract information of complex structures. As observed on this project, we can extract information at any given point of the bridge, and also we can get a full-field mode shape of the bridge. Also, phase-based motion extraction has a good accuracy if compared to traditional sensing techniques. And finally, the integration of the deep learning and artificial intelligence would drastically enhance the damage detection accuracy. So for future and currently ongoing work, we're still working on the data analysis using convolutional neural networks, but we also have a new test planned in a composite bridge in Hampden Mine. So for this testing, we're first considering the camera calibration, such as considering the camera and the lens that we have, the distance that we must be from the bridge to get a full field. In addition, as the recording location for this testing is in a pedestrian bridge that's also under vibration, we're developing a portable data acquisition system based on Raspberry Pi. So we decided to use Raspberry Pi since it can be battery powered, so can be very portable, and then can be together with the camera. In addition, can use two sensors in order to increase the reliability and the redundancy of the data. Finally, thank you for your attention. I would also like to thank for the Transportation Infrastructure Durability Center at University of Maine for funding our research, and to my advisor, Professor Jumal, and my colleagues at the Structural Dynamic and Acoustic System Laboratory at UMass Lowell. Thank you.